So then let's move down to the next speaker, Qixing. So Qixing Huang is an assistant professor of computer science at UT Austin. He obtained his PhD in computer science from Stanford. And then he was also a research professor at Toyota TTI Research before. Okay, so let's welcome Qixing to talk about his interesting talk. Yeah.
Okay, can you hear me?
Yes. Mm-hmm.
Okay, so it's a great honor to speak in this wonderful workshop along with many wonderful speakers. Today, I want to talk a little bit about something slightly different. It's related to relative post estimation. So I want to start off by saying that 3D scene representations are becoming more and more important, including triangular mesh, implicit representation, point cloud scene graph, right? So in particular, in the deep learning era, people have developed wonderful neural networks, deep learning techniques among those representations. Today, I want to talk a little bit about looking at the different representation called multi-view representation, which is quite standard, right? So essentially, we want to look at scene from multiple viewpoints, and essentially, scene is described as collections of images, RGB and RGB-D images. So why this is important? Because this representation directly comes from the sensor, right? For example, all the cameras, no matter it's standard cameras or depth cameras, we all record scenes from particular views. And this representation is also intermediate representation, right? So to other representations, right? So this is called reconstruction, scene reconstruction. And today I want to look at a particular task called under this multi-view representation called the relative post estimation. So this is of course a very well-studied task, but I will soon convince you that in the deep learning era, this task is actually very intriguing. In particular, if we want to represent the scene using a few, not a dense set of views, a few set of views. Okay. So what is the relative post estimation, right? So this talk about focus on RGB-D images. So we given two scans, right? RGB-D images, right? That recorded in a local coordinate system. Our goal here is to find a transformation, which is the T and the rotation, right? So which is R, right? So that describes the relative post between two scans. So this problem, of course, has many applications. So this is just a subset of them, right? So if you're familiar with 3D vision, right? So in multi-view structural motion, we need to estimate the relative poses across the images, right? So for geometry reconstruction from depth scans, right? Resembling fractured surfaces, right? So we also do this relative post estimation to detect loop closures, right? And do this RGB-D basis set, right? So those are very important problems. And in the big picture, if we look at if we talking about the post problem, right? So there are two problems, I should say, right? One is called this post estimation, right? So for objects, right? Because objects we can talk about the absolute post, right? Because objects have front upright orientation, and we can talk about absolute poses. But for scenes, right, for 3D scenes, we don't really have the absolute post problem because scenes we don't really have the absolute orientation, right? So for example, what is the front? Maybe there is upright orientation, but we really do not have the notion of the front orientation, right? So this makes this kind of relative post estimation important, right? Meaning that given two scans, we want to estimate the relative post, okay? Okay, so how relative post estimation is done, right? This is the popular approach, right? So typically what we do here is that we extract some kinds of features, maybe samples of feature points, and we establish some correspondences between the feature points, right? Nearest neighbors or matching descriptors. Then some of the descriptors are wrong, some of the correspondences are wrong, right? So some of the correspondences are correct, and we want to find a consistent one to estimate the relative post, right? So this is before the deep learning era. And in the deep learning era, clearly, I think the pipeline has not really changed, but each individual component has changed, right? So for example, feature extraction, this is not done using handcraft procedures. This is done using, for example, this is FlowNet done using feature extraction towers. And then we have this kind of correlation towers which replicates this kind of consistent feature matching. Okay, so all these techniques are based on the assumption that the scans, right, the images, they don't have overlapping vision, so that we can find shared features to match, right? So here we want to ask a question: can we actually do this even these two scans or RGB-D images do not overlap, right? So we all have small overlapping vision. Okay, can we still do that? So first of all, is this actually interesting test, right? In fact, that if you look think closely, there are many applications that can benefit from the ability of matching scans that have small no overlapping vision. For example, we want to do early detection of loop closure, right? So we want to predict, oh, maybe along this way, there's a potential loop, right? So that we can improve the pose, right? So this is one application. And if we can do this, we can significantly reduce the number of images and observations that are required to reconstruct, for example, very large scene. Okay, and this is also a standard important. There's also important application in solving jigsaw puzzle, right? So, for example, we want to match two patches. They could be stitched together, but they do not have overlapping vision, right? So this is another application. But of course, this is a very challenging task. Okay, this is a very challenging task. Soon we will realize that we need some understanding. Okay, obviously. Okay, so what are the challenges here, right? So challenges here, right? First of all, there are no or few features to match, right? So because they do not really share anything, right? And because of this, black box deep networks would not work, right? Would not work. Okay, and also the overlapping ratios, right? Sometimes overlap a little bit, sometimes those do not overlap, right? So this is something that is very hard to address. For example, if we want to set up a threshold to extract the shared features, this would not work. Okay. So so how should we do this, right? So the motivation comes from here, right? The human perception, right? For example, there's for example, if we want to reconstruct a complete, right, a human 3D model and using two scanners, so one is on the front and one is on the back, right? And we obtain two scans, but clearly they do not overlap. But on the other hand, right, if we ask you to align these two scans, pretty much you can still do it. So why this is the case is because even we only have this incomplete partial observations, so we have the prior knowledge of the entire, right, the shape, right, of the complete 3D human shapes, right? So this prior knowledge, we can utilize this to assemble two scans that even they do not overlap. Okay, so that is the basic idea. Okay. Okay, so the methodology through this talk is that we are trying to combine essentially two types of tools. One is called deep features, right? That is what brought us in the deep learning era. Another is called geometric constraints, right? In particular, dealing with three-dimensional objects, right? So there are a lot of geometric constraints like distance preserving, primitives, and symmetries. But those are the ones that are very difficult to predict using a standard deep neural network, right? The deep neural networks can know good features. But for geometric constraints, they're very hard to predict, right? We need to somehow figure out a way to integrate them together. Okay, so that is what we are trying to do. Okay, for solving this problem. So I'm going to briefly present two papers. One is the first paper published in CVPR 2019. Okay, so the key idea is this is that motivated from the human body example. What we are trying to do here is very simple. First, is that given these scans, what we're going to do here is that we can going to apply a scene completion. Okay, scene completion. Given the completed scenes, then they overlap, right? So then we're going to solve this kind of relative pose estimation. Okay, so I will talk about two important issues here. One is how to do the completion. The second one is how to solve this kind of relative pose estimation. Okay. For scene completion, we utilize the called reduced cube representation. The second paper will talk about something that generalized to this. Okay. So essentially, the idea here is that we're going to use the 360 images, but we eliminate the top and the bottom views. And then we're going to, given one view, we're going to do the completion, right? So to predict the missing visions. And so this is the example on the multiple data set. And then we combine depth, normal, color, nerd, semantic, class descriptors to do the completion, right? So the idea here is that instead of, for example, completing an image, then extract the depth and normal, a normal, for example, that could be very unstable, right? So because the completions are noisy, then the computing normals could be inaccurate. That we pre-compute those kind of different features, we do completions under different representations. Okay. Okay, given those representations, next thing is to do relative post estimation. Okay. So here, what we do here is that we enforce some kind of this kind of geometric consistent constraints that are, right, so enforcing some rigidity constraints. So we combine those features, which also use those features to do this kind of initial correspondence computation. Then essentially the key idea here is that enforce some kind of the geometric consistent constraint, right, which enforce the rigidity between the correspondences, right? So that those include the positional features, including the normals. Okay, so essentially we derive some scope between pairs of correspondences. Okay, so if you are familiar with matching, graph matching, image matching, so this essentially is the pairwise term, okay, that enforces smoothness. But in the 3D case, we preserve some geometric consistency, right? The distance is an angle. Okay. Okay. Then we need to do this kind of matching module, which essentially integrates those geometric constraints to spin out a rigid pose, right? So what we do here is that we combine two types of techniques. So first is this kind of reweighted non-linear least squares. So this is widely used, for example, in local registration, and it's very accurate. But on the other hand, it has a limitation that it can only tolerate 60% of incorrect correspondences, right? So this is a local technique. And then we also have this kind of global technique, which is about spectral matching. So that this is more advanced, right? It solves a spectral decomposition to derive the indicator associated with the correspondences. This can tolerate more incorrect correspondences, but there's no clean separation between inliers and outliers. That can be handled by the first type of the reweighted least non-linear squares. So essentially, our approach essentially combine these two types of approaches, right? So we derive a single optimization formulation, solving the indicator associated with each correspondence. And this can be done by alternating minimization, where we fix the latent rotation translation that's to be recovered, and then we fix the correspondence and optimize this, and we fix the correspondences and optimize rotation translation. So this sounds complicated, but in a deep learning era, people have developed, for example, training strategies for this kind of general feed-forward procedures, right? So this can be trained together with the prediction network. Okay. All right. Right. So this is a side-by-side comparison between the different techniques, right? So for example, we have this is the result of spectral matching. And if we only do this reweighted non-linear least square, it's incorrect. But if we combine them, right, so this gets a lot better. Okay. All right. Okay. But are we done? Right. So the question here is that, right? So this is a very simple approach, right? So we do scene completion, and then we match. Okay. But the question here is that can we actually do better? Okay. So it turns out that there's a generic constraint, right? In the sense that this is also true for multiple inputs, not just two. Okay, is that if we think about complete scene, right? We have two observations here. When we do the completion, right? Even though we don't know the relative pose between them, But essentially, we have the constraint that the completion should contain the second thing, right? It should contain the second thing, even though we don't know the pose. Okay, but we know that after transforming the second scan by some retransformation, it should be consistent with the completion. Right, so that is really the difference between having a single scan we do completion and having two scans we do completion. That is the difference. Okay, and we can integrate this using an iterative procedure. Right, so essentially what we do here is that once we done the completion, we estimate the relative poses, and we can transfer the second scan, right, and combine this with the first scan to improve the completion. Right, so this can essentially improve the completion results and also the relative pose estimation results. Okay, right. So how does this work in practice? We evaluated this on three data sets. Right, so we divide the scan pairs into three regimes. Right, so essentially large overlap. Right, so this is the regime where the standard techniques work very well. And we have the small overlap, an overlapping ratio between 10% and 50%. And then we also have this kind of very challenging setting, right? No non-overlap, okay, non-overlap, okay. And we report angular error and absolute translation error, okay, on three data sets, right? So this is the large overlapping region. Surprisingly, is that even under this region, we still improve. Okay, from the base, right? So this kind of non-deepening baselines quite a bit. Okay, quite a bit. To the small overlapping region, the improvements even more. So large overlapping, we can still have some reasonable results. Okay, reasonable results meaning that first of all, you can see that the deep learning, right? So just doing applying a black box deep neural network. This will not learn the useful features to estimate the relative pose, right? So this is very similar. The performance is very similar to a random guess. Okay, random guess is not 90 degrees. Okay, it's slightly above that. Okay, 120. Okay, random rotation. And applying this thing completion, we can improve this considerably. And I should say that the most of the error comes from symmetries, okay? Because if we have non-overlapping, for example, like whether two, for example, we have images of two walls, right? Whether the walls are orthogonal to each other or perpendicular, right? So we don't have that. And if we consider the top, right? Not the top 1 and top 3, top 5 errors, in particular, the rotation errors will be reduced, okay? Right, so those are some qualitative results. Okay, so I want to talk about the second paper, which essentially extends the first work. This is more interesting from the 3D understanding perspective, right? So essentially, now we know that we need to do the thing completion, but the question here is that what is the right representation to do the thing completion, right? Because relative pose estimation is a low dimensional output, and the question here is that do we really need this kind of dense completion, right? The completing every single pixel, right? So if we analyze, for example, the quality of the completions, right? So this is the right? So essentially the distance, right? The x coordinates with respect to the center of the camera. You can clearly see that the completion result. If we do this dense completion, right? The completion result, the quality drops, right? When the pixel is far from the visible region. But on the other hand, is this the optimal representation for scene completion for the task of relative pose estimation? So in the second paper, we try to combine essentially different representations, right? We combined a this kind of cube map representation that is what we used in the first paper. Then we study the two other representations, right? The top view, this is a two-dimensional representation that can capture the spatial layout. Then we also have this kind of planar features, which are very popular in those things, right? So essentially you can think about this, right? So in particular, plane features tend to generalize better in regions that are far from the camera point of view, okay? All right. So what we do here is that we combine these three type of representations to extract features, but still we use the matching module to automatically select the features to match. You can imagine that for certain things, right, in particular, if there's a large overlap, the cube map representation is good. But then if the two views are very far from each other, then this kind of planar features, right, tend to be better. Okay, tend to be better. Okay, right. And the selection of the feature is automatic, right, by forming a spectral matrix, right? So essentially extracting the consistent features. Okay. So this is one story. Another story is that I think is very interesting for solving this relative post estimation problem, and also for other problems as well, is that, right, so we have, right, when doing this relative post estimation, we have the global phase and the local phase. Global phase meaning that we do not have the prior knowledge of the relative post between two scans. And in the local phase, suppose we already have some guess, right? Then in the local phase, essentially we can use different representations. For example, the relations, right? So in 3D things, we have a lot of planar structures, right? So this has been used a lot, right, in 3D vision research, right? Here, well, after completion, what we can do here is that we can extract the point pairs, for example, that the perpendicular, that parallel, right? Assuming that we already have some reasonable initial guess, we can use the post to detect those relations, right? So and then enforce those relations to improve the relative post estimation. Okay. So what I want to convey here is that right, the local phase, global phase, right? So there are different features we can different types of features we can use. So what we do here is that we introduce a variational formulation to combine different types of features, right? So we have the pointwise features, we have this kind of plane relational formulations losses. Essentially, we combine them, right, to solve or optimize for the rotation translation. We use a robust formulation. Very interesting here is that this is also very friendly to training, right? For example, here essentially we can enforce that the optimal solution to our optimization formulation is close to the ground truth. And using implicit sanction theorem, we can back propagate the networks to that the loss, right? So the loss training loss to the prediction network that generate essentially these terms. Okay, so this is the details can be found again found in the paper. Okay, so how does this work, right? So we improve substantially from the approach that just uses a single representation. Okay, still this does not fully address the symmetry issue, right? So the top 3, top 5 losses are substantially smaller than those. Okay. All right. Okay. So those are some of the qualitative results. Right. So this row is the result of using a single representation to do the thing completion. And then these are the top 3, top 5 results, top 3 and top 5 results. Okay. Okay. Right, and we can also apply this, right? So once we have a better way to estimate the relative process, we can apply this to multiple views, right? Still a small set of views. For example, here we show 5 views, and using standard techniques to estimate the relative process, this would not work, right? But having the complete thing, using this as a prior, and we can do substantially better. Okay, do substantially better. Okay. All right. All right. So to conclude, so in this talk, we talked about this extreme relative post estimation. The biggest take-home message is that even for this standard task, right, in the few view setting, right? Even they overlap a little bit, right? So having some knowledge of the underlying 3D scene under certain representations, this could be very, very beneficial. Okay. In fact, that in the learning era, there are a lot of work on trying to reduce the number of views for multi-view stereo application, for example. Okay. Still, we need to solve the post problem, and the message here is that even under this setting, right? So learning approach is very important, right? So trying to instill the prior knowledge of the entire scene. Okay, so this is very important. The second, right? So the scene representation is critical. Okay, 3D scenes, right? We have different ways to look at this, right? The feature learning perspective. I think 3D scenes are very interesting in the sense that there are a lot of geometric primitives, okay, okay, that are very, very, those representations tend to be complementary to the representation like 360 images, right? So this kind of dense representation, right? So right? So they encode different types of the properties of the 3D scene, okay? Right, so hybrid representation is very important, right? So essentially in the second paper, we talked about combining different representations, okay, feature extractions on different representations. And also there are different representations for global mesh and local registration. And what does this mean is that for different tasks in 3D scenes, right? So we tend to write different representations, right? That tend to be beneficial for different tasks. Okay, so I also want to advertise that I recently gave, if you're interested in hybrid 3D representations, you can look into my 3D GP talk. I recently talked about this. This is somehow complementary to what I talked about here. Okay, and I want to acknowledge my the funding agencies. I'm happy to take questions. Okay.
Yeah, thank you, Qixing. Pretty nice talk. Yeah, so let's see if we have any, if the audience have any questions. Yeah, just feel free to raise the hand or also type it in the chat box. But I also have an interesting question. I also have a question about your relative post estimation. So
Yeah.
you mentioned a task where there's no overlap. In my sense that if there's no overlap, it's more like kind of guessing, or yeah, I'm not fully kind of convinced by the intuition that we need to kind of register point clouds that have no overlap. So for me,
yeah, so the overlap is that, right? So there's a visible vision, and so essentially we do have some prior knowledge, right, of the in the neighborhood of the visible vision, right? So essentially, by extending this, we can allow the we can relax the constraints, okay, of enforcing that the scans should overlap. So why this is interesting, for example, even for example in interactive scanning, right? So this application, right? So you may say that we have this kind of consecutive scans, we don't need learning, we don't need this meshing, right? Yeah. But in many cases, for example, like when you stop and go to another, right? You stop another like string, right? So and there are a lot of discontinuities, right? So during the interactive scanning procedure, where we have to solve this kind of matching problem, right? Sometimes the scans do not overlap. Okay, for example, when we scan the teeth, right? We scan this side, we move to the other side, right? And we do have some prior knowledge of the underlying object, right? So, but somehow, right? So for to have a very friendly user interface, we do have to solve this problem. Okay. I
see.
And we call this extreme relative post estimation is to, we do not want to say, hey, they should overlap 10%, for example, right? So sometimes they overlap a little bit, sometimes they do not overlap, right? So this just to give some freedom, right? In particular, in the field view set, in the field view setting, we may have areas that are not covered by the input view. Right?
Yeah. I think there are many interesting applications. For example, if there there are many. So if you're handling a few cameras and you do not want to have too much cameras in your room for kind of surveillance, for example, the surveillance cameras, you may only want to two and they may not have too much overlap. And in that case, maybe it's better if you can kind of match them, even if they have no overlap. Yeah.
Yeah.
Yeah, I think there's also a question from Yan Xia. He's asking, is this completion a semantic scene completion? If semantic information is added, so will the effect be better?
Yeah, so this is a very good question. So we do have a semantic descriptor as a channel for completion, right? In addition to color, depth, normal, right? We do have a semantic descriptor, and that helps a lot in terms of pruning the initial correspondences.
Okay. Yeah. Thank you. Thanks for the talk, and also know that you have recently have a really interesting research around like hybrid representation and also this kind of relative post estimation. Yeah. Look forward to your future work.
Okay. Thank you.
Yeah. Okay. Thank you.